So now, with the counting method, we have to know the codon table. We have to memorize it, or at least you have to look at the codon table. It's a lot of time to do one after another. So Professor Wenxiong Li proposed a way to estimate it. And that is also very straightforward from your codon table. So he proposed, let's separate the site into 3 categories. One is 0, that means non-degenerate. Okay, he used a different word. Degenerate means, when we learned codon table in our biology, we say there's a degeneracy. Means if the position change to a different one, it doesn't matter. It doesn't change the amino acid. So that is how we use this word for the codon table. So if there's no degeneracy, means change to any other type of nucleotide, it change the amino acid. So that's the 0 degeneracy. All the possible changes are non-synonymous. Then there's 2 for degeneracy. So 2 for degenerate site is there's only one type of change, because for each nucleotide can change it to 3 different nucleotides, right? But there's one which remains the same amino acid. The other 2 will change to a different amino acid. So for the one, like for each column, there are 2, 2. For those amino acids, like a phenylalanine we just mentioned, it's a 2 for degenerate site. And then the third one is the 4 for degenerate. So the 4 for degenerate is the one which you can change all different nucleotides, right? And they remain the same amino acid. So that's the 4 for degenerate. So for any given sequence, you can do the 3. There's only one. It's a little bit difficult. It's the isoleucine. Isoleucine is a 3 because there's one occupied by methionine. Okay, so for that one, we count it as a 2 for degenerate sites. So that's the only one you have to worry about. All the others, it's straightforward. It's either 0 or 2 or 4. So he used the notation L0, L the length, 0 non-degenerate, 2 to 4 degenerate, 4 for degenerate. Then the same example, you can take a look. Why he did that? Because it's very easy to find out the property of the changes. In most cases, the changes remain the same amino acid. It's a transition. The changes the amino acid. It's a transversion. So you can see in this slide, if it's a 2 for degenerate site, you can easily look at it's a transition or a transversion. For 4 for degenerate site, it doesn't really matter. So that's the property he's going to use and to estimate the number of sites and number of changes. Okay, so for 2 for degenerate site, you have to check the property of the transition. So you have to know the transitional differences and transversional differences contribute to the changes of the amino acid state. So that's the thing he tried to do. So the proportion at I for degenerate sites, then they use a notation, use S and V, that's the transition and transversion, and divided by the total length, the total number. So simply, he can use this method to estimate the proportion of transitions at this type of site. So when I say this type of site is 0, 2, or 4 for degenerate sites. So this is how he tried to simplify the ways how we estimate the synonymous and non-synonymous. So here is what he used and applied the Kimura two-parameter method. So you have transition and transversion per different type. So the formula we calculate the K, the substitution rate is on the top. That's the one, regardless whether it's a coding or non-coding sequence, we can use this formula. So this is the one we talked last week, and I remind you like very early on today's lecture. Then we can calculate A and B separately. So transition is A, transversion is B. Then I is 0, 2, or 4. Then of course, there's only transition and transversion. So if you plus A and B together, they like sum them together will be the K. Then you also know for each type, what's the proportion for transition and transversions. So that's something you have to put into the model. So now you can calculate I equal to 0 or 2 or 4. Actually, the 2 is the most important one. I just show you the codon table. So A2 and B2 is the number of synonymous and non-synonymous, right? So for A2 and B2, A is the synonymous at 2,4 degenerate site. B2 is the non-synonymous at 2,4 degenerate site. And how about 4? Of course, you can calculate A and B transition and transversion. But this is something rather simple because any changes at 2,4 degenerate site is a synonymous. So in this case, this K4 defined as the synonymous substitution rate. And how about 0? 0 is the one, no matter what changes happen, it's always a non-synonymous substitution. So once he separates into the 3 categories and separate further by synonym, non-synonymous, you can easily see K4 totally contribute to the synonymous side. K0 totally contribute to the non-synonymous side. Only the K2, you have to separate A2 and B2. One is synonymous, the other one is non-synonymous. So this is like you can, just by looking at the position of the sides and also knowing whether it's a transition or transversion, you can calculate all the possible type of changes. Then you can put on the formula about the synonymous and the non-synonymous. We use Ks and Ka to say, so Ka over Ks is from here. So you see A and S stands for the synonymous changes and non-synonymous. S is the synonymous change, A is the non-synonymous change. So you can calculate that. So at the bottom is to look at L2, so 2,4 degenerate side. Think about there are 3 possible changes. One is transition, the other 2 is a transversion. So here has a quarter of L2, 2/4 of 2 contribute to either the synonymous changes or non-synonymous changes. And L4 and L0 is simply one is non-synonymous, the other is synonymous. On the top is the type of changes. So it involves all the transitional changes is on the top, right? So A2 is on the top for synonymous changes. B2 is the transversions. They are all non-synonymous, contribute to Ka. And The other part is easy. The other part just like the total number. 4, 0, or 4, 4, 4, degenerate sum. So that's the way Lee proposed how we can calculate or estimate the number of changes based on its degeneracy. Okay, so this is another version. So most of your computer program now use the Lee 93 method. This is the one. So this is proposed by 2 different papers published some almost independently. Then they just look at the formula previously proposed and modify it further to get the number here. So now you don't see the 3/4 or 1/4, something like 1/3 or 2/3 here. They simplified the estimates by like these 2 formulas to estimate the synonymous substitutions or non-synonymous substitution. But the idea is very similar. It's the same as previously. Just look at the transition transversion, look at the degeneracy of each site, then you can estimate, based on the multiple hits model, you can estimate the substitution rate.